I think you can see my screen.
Yes.
Is it clear?
Yes.
Okay. Okay, so welcome to this session, and it is with a pleasure to be with you today in order to deal about how we can find the shortest hole drilling path in printed circuit board using a new approximative method. In fact, very recently we invented this new concept of optimization method entitled as Dhouib-Matrix. Well, let's consider this example. Here we have a printed circuit board and we have 442 holes to be drilled. Sure, we will use a computer numerical controlled machine where there is a robot arm, and for this robot arm we'll start from this position and need to visit all those holes and return to the starting point. This is a very complicated process because the domain space is very huge. So we need some optimization methods in order to generate a planning for the robot arm. Because if we minimize the movement of the robot arm, we will increase the productivity of the computer numerical controlled machine. So we need here some kind of optimization methods in order to generate a planning for hole drilling path. Then we will use G-code to translate the planning of all drilling path to the computer numerical control machine. So our contribution is here. We invent new optimization methods, and in fact, those methods are gathered as heuristics, meta-heuristics, and also we designed exact methods. Those methods are applied for several kinds of combinatorial optimization problem, but today I will present only one. So the first one is about generating a starting point using the heuristic DMTSP1. So here I will show you step by step how we can generate good initial basic feasible solution. Then I will present our local search method entitled FireTuner. Then the third method will be presented and entitled as Dhouib-Matrix 4. So my presentation is structured as follows. First, I will describe the hole drilling problem as a traveling salesman problem. And rapidly I will present a mathematical formulation. Then the three proposed methods, the DMTSP1, the FTN, and the DM4. Finally, I will conclude and I will present our next work. So let's begin with the description of the hole drilling problem as a traveling salesman problem. So look here. Let's assume this example about 76 nodes, where the blue square here represent the cities. And you will see that it's the same problem. We have a salesman who need to visit all those cities only once and then return to the starting city. So this is like drilling holes and minimize the movement of the robot arm. This problem is present a huge number of realizable solutions. Look for 76 nodes, and for asymmetric problem, we have this number of realizable solutions, and we are looking to generate the optimal one or near optimal one. Mathematically, this problem is modelized as follows. We are looking to minimize the distance ig multiplied by xig, where xig is a binary decision variable. Be careful for this problem. It is not as simple as its mathematical formulation. So this problem is very complicated. It presents a complexity of big O n factorial. And the TSP, there is many application of the TSP as the drilling hole problem, which I will deal about that today. And we apply that also for drilling foot separator screen like this. And we can apply also this problem for production planning, where we have different parts are to be manufactured on one machine. To do this, the machine has to be converted several times, where the states of the machine correspond to the cities and the changeover times correspond to the travel time. And we are looking also here to minimize over changeover time. For this kind of a problem, there is several heuristics. Just for example, here we can apply the Hungarian methods, which are basically designed for assignment problem or also one assignment. And here we invent two heuristics, the DMTSP1 and the DMTSP2, and also several meta-heuristics are adapted to solve this kind of problems, such as genetic algorithm, BAT algorithm, variable neighbor search algorithm, and colony optimization, artificial bee. And here we invent three kinds of meta-heuristic, the Fortunier, the DM3, and DM4. So as I told you, I will start with, today I will show you three methods that we can use it to solve this problem. And I will start with this first method entitled DMTSP1. We invent this method in 2021. This method is very rapid and it is a good initial basic solution. And I will show you step by step through an example how we can solve this problem. So let's start. So in order to optimize the traveling salesman problem here today for us, the drilling, finding the shortest drilling hole drilling problem in polynomial computational time. So this method was developed in 2021 and present a complexity of big O n. In fact, we need just to iterate n-1 iteration, where n is the number of holes. We published several papers in this using this concept. You can just Google a bit and write the Dhouib-Matrix TSP1 and you will find several papers. This method is very sampled. It needs just 4 sample steps. And I will show you through an example how we can apply this method. But here just to explain that if I will discard step number 4, we will generate the shortest path problem and not the shortest cycle problem. What here is the main difference. So if you will, I will execute the 4 steps. I will generate the cycle. I will generate a cycle like this between all cities. But if I will drop step number 4, I will generate the shortest path joining all cities. So this method, this is amazing method. If you will apply all the 4 steps, you will generate the shortest cycle. Otherwise, you will generate the shortest path and not a cycle. Today, we will use only 3 steps and how we can generate the shortest path. So let's take this example. And through this example, I will go step by step and I will show you the application of the novel method Dhouib-Matrix TSP1. So if here there is 9 holes to be drilled, represented here by red circle. For each circle, we have the coordinate x and y position. So from this position, we can use any function. And for example, here we can use Manhattan metric in order to compute the distance between all the cities. And for this problem, look at the number of realizable solutions to 2106 realizable solution for this problem. How we can solve that? So let's start with the Dhouib-Matrix TSP1. So the first iteration here is to compute for each row the first quartile. This method is very flexible. You can use sum, mean, any descriptive statistical metric. And today I will use the first quartile as a metric. So we will compute for each row the first quartile, then I will select the smallest one, which indicate row number 8. So I will return to row number 8, and I will select the smallest element in row number 8. So the smallest element is at this position, which represent the elements at the position 8 and 5, which means we will generate, or the robot arm will go from whole number 8 to whole number 5. So I will insert in these cities. Here I will insert the list or the order of the holes to be drilled. So at the beginning, I will insert hole number 8 and hole number 5 at the bottom at the list city. And to eliminate the return to these holes, we will discard column number 5 and column number 8, because we are looking here to generate an Hamiltonian cycle. That means each holes will be visited only once. So here we finish with the first iteration. We will go to the second iteration. For this problem, we have 9 holes, so we will solve this problem just after 8 iterations. So here we will start the second iteration. So we will, for the first element in the list city, which indicate row number 8, we will select the smallest element for row number 8, which at this position. Then we will consider the last element in the list city, which indicate row number 5. So directly we will go to row number 5 and select the smallest element, which here at 34. Next, we will select the smallest element between 34 and 32.9, which will be this element at the position 8, 7, which means the robot arm will go from hole number 8 to visit hole number 7. So as you can see, we are generating an order or a planning of the movement of the robot arm. So here we will insert city number 7 just before city number 8. And we discard column number 7 because we visit these holes only one. And we finished with iteration number 2. We will go to iteration number 3. We repeat the same thing, select the smallest element in the row number 7, and we repeat the same thing for row number 5, select the smallest, which at the position 5, 4. So city number or holes number 4 will be visited just after hole number 5. Then we will insert here just hole number 4 at this position. And you can see here we are generating an order to visit for the robot arm. And we will discard column number 4, and directly we will go to iteration number 4. The same thing, select the top element in the list city, which represents 7. So I will go to row number 7, select the smallest. then the bottom element, which indicate row number 4, select the smallest. Here we have the same values, so you are free to select anyone. And we will select, for example, this one, which indicate that hole number 6 will be visited after hole number 7. So we will insert here the order, which indicate that hole number 6 is visited just after hole number 7. And to eliminate, to return to hole number 6, the same thing, we will discard column number 6. Now we are with iteration number 5. We'll repeat the same thing. Select the smallest element in row number 6, row number 4, select the smallest, and add this at the top of the list cities and discard column number 1. Then we will repeat the same thing, and as you can see, my list of city will gather all holes, and we will finish with this one. This smallest one is at the position 4, 9, which indicate hole number 9 will be visited just after hole number 4. And here we have the order of the movement of the robot arm. Just we will plot this solution as a graphical presentation as here, and we will return the first one. So the first hole to be visited is 3. So the hole number 3. So the robot arm will start by drilling this position. Then it will be hole number 2, which is represented here, hole number 2. So this, then hole number 1, next 6, 7, 8. So 6, 7, and 8, and so on. And here we give the order of the robot arm in order to which generate the shortest drilling or hole drilling path. Okay, the first method, the MTSP1, is just used to generate an initial basic feasible solution. But for more larger instances, we need use more sophisticated methods. Here we developed a local search technique. We call this as Fartonier technique. It is a local search method based on 3 sample structures, an organized neighbor selection, 3 perturbation techniques, and threshold accepting criteria. And here just an example of a 3 perturbation technique: insertion, exchange, and 2 opt. And we apply for Fartonier method for other instances, like here for this sample example of 14 holes to be drilled. Here another example of 49. And the example of 442 nodes using the solution generated by Fartonier. Also, we can use this method to select the starting point of the robot arm. Otherwise, what if the robot arm will start at this position, and what will be the solution? And what if the robot arm start at this position, and what will be the solution for this kind of problem? Now, for more larger instances, we generate a multi-start technique. We call this as the M4, and the M4 will combine the 2 techniques: the first method, the DMTSP1, and the Fartonier. So the Dhouib-Matrix 4 will gather the 2 first methods. So the DMTSP1 will use it just to generate an initial basic feasible solution. Then this solution will be intensified by Fartonier. And this is a multi-start. That means we will repeat that several times. Look here, using mean as a metric. Here, if I will use max, I will select another initial basic feasible solution. And the example that I presented is just a key one of the first quartile as a metric. So with the Matrix 4, this is multi-start technique, which combine both of the methods. And this method generates a wonderful balance between diversification and intensification, where diversification is assured by the Dhouib-Matrix TSP1 and the intensification by the local judgment technique. Here are some solutions generated by the DM4, and you can see the relative error to the between the genetic algorithm and the DM4. Look here at the comparison between ant colony algorithm, simulated annealing, particle swarm. So we apply DM4 for several instances from TSP library, and we compare it to other methods using integer distance and also using with real distance. And here you can see the comparison to the ant colony algorithm, which presented here with the blue one. DM4 is this representation. We apply also DM4 for other instances here for 296 holes in main board of a Pentium 2 PC, and we are looking to generate the shortest path to drill the holes in this main board of a PC. Just here a comparison between the generated solution and the DM4. Also, we compared DM4 to other instances here about drilling 2,152 nodes in motherboard of PC. This is a last published paper dealing about generating a shortest path. So here it is an open TSP and not generating a cycle. And just look at the comparison of DM4 to ant colony, to artificial bee colony, to genetic algorithm. And for this kind of problem, we found the best value. Literature, no one find this kind not find this solution. So to conclude, very recently in 2021, we invent a new optimization methods, which gather heuristic, meta-heuristic, and also exact method. Today, rapidly, I presented the three techniques, where in the DMTSP1, I show you step-by-step application, how we can generate an initial basic feasible solution, and the Fortuner. And for larger instances, we need the DM4, which combine the DMTSP1 and the Fortuner technique. Just we deal about that DSP. If we execute the 4 steps, we generate a cycle. But if we will eliminate step number 4, it will be a shortest path. What is next? We are looking to apply the DM4 for multi-objective environments. And also very recently, we invented this kind of method which generates the shortest path between pair of cities, or single source shortest path problem and single destination short path problem. We call this method as the matrix SPP1. Thank you for your attention. Is there any questions, comments, remarks?